Seeing my previous video, in which I was struggling with installing ViOS on our custom board, a friend reached out and told me I went way too fast with both presenting the problems I faced and the fact that many of our peers are missing the foundational knowledge about how these things work together. So I figured, you know what? I'm just gonna make a video in which I explain how custom ARM boards are booted basically from the ground up. And this is that video. Before we begin with the more hands-on part of this video, let's first discuss the possible ways that embedded devices have their storage connected to the CPU and what kind of storage that is. Now, keep in mind that this isn't an exhaustive list and there are numerous other ways, but since I'll be working with our NXP reference design board throughout this video, well, my process is gonna be somewhat adapted to it, but worry not, most of the steps I'm going to take apply to the majority of other embedded boards as well, and I'm going to give you plenty of heads up at things that are particular to our board. So what are these three options that I'm talking about? First, and I'd argue also the most common one, is the eMMC chip. eMMC stands for Embedded Multimedia Card, which is actually exactly the same chip that you can find, say, in SD cards. The only difference being that the E part, which tells us that, well, the chip is soldered onto the PCB and is thus not removable. The convenience that eMMC brings to the table is that apart from the flash storage itself, it also contains a dedicated controller that's responsible not only for reading and writing to the chip, but also things like wear leveling and power loss protection, which flash storage is very sensitive to. Wear leveling, in case you didn't know, is a way of writing to the flash where you try to write to all the blocks as equally as possible so that all of them have a similar number of writes on them. Throughout the lifetime of the device, that is, because as you probably know, flash cells wear out over time and writing to them is the cause of that. And here is where wear leveling comes in. It ensures that they all degrade at an equal pace and thus prolonging the lifetime of the device. And since eMMC chips already ship with all these features built in, it makes them the most convenient type of storage because they only have to expose the MMC bus to the CPU, and Linux, our operating system of choice, already has drivers in place to talk to them out of the box. From a mechanical perspective, this bus only needs 3 wires, and when I say wires, I mean traces on the PCB to connect the CPU to the eMMC chip. These 3 traces are command, clock, and at least 1 data trace. We won't talk about the command and clock because they're too low level for this video. The only thing you need to know is that they're a way of syncing 2 chips. Data trace, on the other hand, is how data moves back and forth between the two, and if there's only 1 pin on the eMMC connected to the CPU, then we call it a 1-bit bus. Now, because the eMMC protocol is fairly slow, people much smarter than me figured we should connect the chips with more traces than just 1. So most eMMC chips today support up to 8 bits, meaning they have 8 pins available to be connected to the CPU, because an 8-bit bus, all other things being equal, is 8 times faster than 1-bit bus. And yes, we as PCB designers do not need to connect all of them. An eMMC card with 8 data pins will work just fine if only 1 of them is connected to the CPU. And in fact, when the device boots, that 1 pin, or rather the data that goes through it, is responsible for negotiating the right speed between the CPU and the eMMC chip and consequently turning the rest of the lanes on. The next, somewhat less popular choice for embedded storage is then the raw NAND flash. Think of the eMMC chip that we just spoke about, remove the controller, and what you're left with is exactly that. And I think it's quite obvious why it's less popular, because in order to read and write to it, you need to add a controller yourself, be it one that's integrated into the CPU or as a separate chip. In either case, this adds cost and complexity to the PCB. A complexity that, outside some very niche use cases, doesn't really solve any problems, so even we were recommended to stay away from this approach, despite the fact that our CPU does come with an integrated flash controller. And this brings us to the last type of flash storage that's used in the embedded world, and that is NOR flash. Unlike NAND flash that we can find in the eMMC chips, NOR flash is actually much more durable and performant, but because of that, it comes at a much higher price. You see, 64 megabyte chips that we have on our board, for example, cost around $5 each. Yes, that is 64 megabytes. On the other hand, a 32 gigabyte eMMC chip costs around $15. So why use them at all given their small capacities and high price? Well, because of their durability and resilience, they come handy as a sort of a rescue device, so to speak. Imagine your eMMC gets corrupted for whatever reason. If you have no NOR flash on the board, then congrats, you have a very expensive paperweight until you find somebody with specialized equipment that can help you sort things out. But a 64 megabyte NOR flash chip is just large enough that it can hold not only the bootloader, but also a tiny Linux distribution with just enough of the basic tools that it can help you fix the eMMC problem yourself. Now, does that mean that it would be possible to have an embedded device with just the NOR flash chip? Absolutely. If the device needs only some basic functionality and will likely not be user accessed throughout the lifetime, then why not? Okay, now that you know the basics, it's time to get our hands dirty. I'll pretend as if our development board is completely empty and pretty much built all the necessary software and firmware for it to run from the ground up. I will cheat a little because luckily for me, our reference design board does come with 2 NOR flash chips, so I will be able to perform work on the second one while being booted into the first one. This is actually quite uncommon because NOR flash is usually the last resort, which means the firmware is already flashed onto the chip in the factory and you're not really meant to mess with it. Because if you do and you mess it up, you end up with a brick device. Now, at this point, you're probably wondering, how is this done without me being able to cheat with 2 NOR flash chips? For that, my dear viewer, devices like this one exist. It's called a JTAG programmer, and you plug one side into your development PC, and the other side has a special cable that connects to the JTAG headers on the board. Then, what I need to do is prepare a complete bootable image, and finally, flash it on the board using this JTAG programmer that costs several $100s, through software on my PC, licenses for which cost thousands of dollars. Indeed, it can get very expensive. Okay, now that you know the ways we can flash our NOR chips, the first course of action for me will be to plug the console cable into the port that says, unsurprisingly, console. This is just your regular USB cable because my board already comes with a chip that converts USB to UART, which stands for Universal Asynchronous Receiver/Transmitter. What I have to do next on my Mac is just run the screen command, give it the correct parameters, and voila, we're connected to the device. But we can't see anything yet because, well, we need to first turn it on. If you don't understand what you see on the screen right now, worry not, we'll go through it together. At least through the most relevant bits here, which are the 2 separate bootloaders. See here on the top, the lines that start with BL2? Well, BL literally stands for bootloader, and this is the second one in boot sequence because the first one is actually in the CPU itself and we cannot access it. But suffice it to say, its main responsibility is to activate the correct protocol and pins on which it expects it will access and run BL2 code. And in our case, these pins are connected to the NOR flash chip. BL2 only has a single responsibility, and that is initialization of RAM, which is why, when it's done, it immediately boots into BL3. Don't get confused here, despite the fact that it says BL31, you should really think of that one as the first part of bootloader 3 and not bootloader 31. What happens next is that the bootloader 3 runs U-boot, which, to complicate things even further, is in BL33, although you can't see it on the screen. And yes, BL32 exists as well, but we don't use it here. I'll leave a link down in the description if you're curious as to what it does. So now we're in U-boot, which is the first environment that we can actually interact with, and we will. A lot actually at this early stage. See the line that says boot from QSPI VBank 0? This is specific to our board we're working on, and as I explained earlier, our board ships with 2 NOR flash chips so that we can work on one of them and possibly even mess it up while the other one is in fully working state. So let's completely wipe the second chip so that we will build everything absolutely from scratch. First, we need to tell U-Boot what chip we want to work with, and in our case, that chip is on the bus 0, position 1. So we'll enter sfprobe 0:1. How do I know that? Easy, because I read the documentation that our CPU ships with. Now that we're focused on the correct chip, it's time to wipe it, so we'll enter sferase 0x0, 0x4 and 7 zeros. And while we wait for it to complete, time for some theory, because you will see me using this notation quite a lot throughout this video. You see, memory, regardless if it's volatile or not, has addresses at which it stores data. And these addresses are written in hexadecimal values indicated with a 0x prefix. They might seem confusing at first, but all you really have to do is convert them to a decimal number and you get their position in bytes. And you know what the fastest way to do that is? You ask ChatGPT. So how much is 0x4 and 7 zeros in megabytes? 64. Which means we just erased 64 megabytes, starting at 0, of our 64 megabyte NOR flash chip. And now that it's empty, let's leave our board for a bit and build both bootloader 2 and 3 on our development machine. In my case, I'm using a virtual machine on my M1 Max Studio, which saves me the step of needing to cross-compile for ARM64 architecture, but I'll leave a link down in the description to a PDF that will guide you step by step on how to install all the necessary tools to cross-compile for ARM64 on your x86 Linux machine. This episode is brought to you by PCBWay. I've been working with them on my custom keyboard project and I was super impressed with their speed, quality and price, so I'm more than happy to recommend them to anyone who needs any kind of PCB manufacturing done, whether it's just for a couple of prototypes or if you need a larger production run. Link to their website, of course, down in the description. Back to the video. The first thing we need to do is download U-Boot and build it for our board. We'll use Git here and just clone from the official repository, and also very important, I'll switch to the latest stable branch, which as of the time of this recording is v2024.07. In order to save us a lot of time actually, U-Boot already ships with configuration for the most popular boards out there, so all I literally have to do is run the command make, followed with the name of the configuration file for our board. So ls1046 ardb tfa defconfig. Now that is a mouthful. We can find this file if we list them in the configs directory. The result of this command then, as you can see here, is a .config file, which basically tells the compiler how exactly to build the final image, which it does when we run the make command with a parameter -j8. This parameter tells the compiler we have 8 cores at our disposal so that it can use all of them and thus speed up this usually very lengthy process. Perfect, U-Boot is now built, and yes, this is all it took. Now, obviously, we can always go into U-Boot configuration and tweak things here and there, but the defaults are already recommended by the manufacturer, so we're going to stick with them. Now, if you recall from earlier, U-Boot is not the first bootloader in the stack, so let's build that one as well. The repository we need to clone for that is called ARM Trusted Firmware, and much like with U-Boot, we need to switch to a stable branch, and in my case that is LTS v2.10.4. Now, before we actually build it, we need another piece of firmware which is particular to our board and is also supplied by the manufacturer NXP. It's called a Reset Configuration Word, or RCW, and what it does is it configures general purpose SerDes lanes on our CPU to what the board has connected to them, because if you've seen some of my previous videos, SerDes lanes can be connected either to a PHY chip for networking, a PCIe device, well, for whatever you choose to use it for, or finally a SATA drive. Interestingly enough, there is no configuration needed here because compiling the binaries with the correct parameters will already produce exactly what we need in a way that is ready to be used on ARM trusted firmware. So let's go back to that directory and run the following command. I won't go into details here because this is literally taken from the official documentation, and I think most of it is pretty much self-explanatory. We're building the BL2, which we want to boot from QSPI, which is the bus that the NOR flash chip is connected to the CPU with. And finally, we're also passing the reset configuration word we just compiled. Okay, see that BL2 underscore QSPI.pbl? That is the completed bootloader 2 firmware. What I'll do next is I'll copy it into where I've set up a TFTP server, which is /srv/TFTP. We need a TFTP server because U-Boot has some very convenient ways to download firmware from one, so I'll leave a link to a tutorial on how to set one up down in the description. It literally takes like 3 to 4 commands. Now that we have the bootloader 2, let's also build the bootloader 3 and use the same ARM trusted firmware to do so. Again, this command comes from the official documentation, so if you're curious about any part, check the link in the description. And like I've done for bootloader 2, let's copy this file to our TFTP server directory as well. Almost there, I promise. The final piece of code that we need in order to run U-Boot are also the drivers for our network interfaces that come built into the CPU, and the umbrella term on our board for all of them is called Frame Manager. These drivers are already compiled and uploaded to NXP's GitHub repo, so all I have to do is literally just clone it and copy the correct file to my TFTP server. There we go, we now have everything we need to flash our NOR flash chip. So let's switch back to the board, download all the binaries and finally flash them onto the chip we erased earlier. Again, let's first make sure that we select the correct flash chip so that we don't accidentally overwrite any data on the one that we're working from. Then, before we can actually write anything, we need to configure networking by setting both the IP address of our board and the IP of the TFTP server, both of which are set with environment variables. Now that we have those in place, let's first download our bootloader 2. The command to do so is actually fairly simple to understand. We run TFTP command, and because we have the server IP environment variable in place, it already knows what IP to connect to. Then we have a memory address, as in where we want to temporarily save the file, and finally the name of the file on the TFTP server. Okay, half of the way there. The only thing we now have to do is write the contents of that file from the memory and onto the NOR flash chip, which is where it will be stored permanently. For this, we will use the following command. Again, I think fairly straightforward. We write to the chip we probed earlier from the same memory address we downloaded it to, and use the offset 0 on the NOR flash, as bootloader 2 needs to be the very first thing that the CPU reads when booting. The last bit, file size environment variable, was automatically set with the previous TFTP command so that the write command copies over just the necessary amount of bytes and not a single byte more. Excellent, no errors reported, which means we're all good. So now let's repeat the 2 commands both for the bootloader 3 and for our Ethernet drivers. The keen-eyed among you probably noticed different offsets on the NOR flash where we need to write them to. And yes, they need to be written at different positions, and these positions can be found on the datasheet where it says memory layout. Again, the same principle applies. The offset of 0, x, 9 and 6 zeros is exactly 9 megabytes from the start of the flash chip. Again, if unsure, ask ChatGPT. Okay, the moment of truth. I'll enter a command with which we will reset our board into this newly flashed NOR chip. But keep in mind that this command is particular to our board. The FPGA chip that allows me to do that is called CPLD and is meant primarily to allow me to mess things up with the bootloaders and still be able to reset the whole board into either a working chip or even an SD card if I mess both of these up. Normally, production boards don't have that luxury, primarily because it would make them more expensive and also because bootloaders usually aren't built to be tampered with in the first place. The command I'll use here is called CPLD reset old bank, which will trigger this FPGA chip into reconfiguring the whole board so that the CPU boots into the alternative bank that we just worked on. There we go. There are several indicators here that let us know we succeeded, apart from, you know, the fact that it booted in the first place. The first one are obviously the versions of both BL2 and U-boot, which correspond to the branches of the ones that we switched to earlier, if you remember. Then we have a line with the board name that also indicates that we're booted onto the alternative NOR flash chip, which in my case is marked as QSPI VBank 4. Why 4, given there are only 2? No idea. Ask NXP. And finally, it can identify all the Ethernet interfaces, which means that we correctly uploaded the firmware for them as well. Now, one question you might have is, we have a 64 megabyte chip, but we're only using like a little more over 1 megabyte of firmware. Isn't that a waste? Or to put it differently, could we have put the firmware onto different offsets, then use a NOR flash with much smaller capacity to, you know, make it cheaper? Absolutely. The offsets I used in this video are just the defaults that our board ships with, but I can easily reconfigure U-boot, for example, to look for networking drivers elsewhere. One final thing I should also mention here is this warning, which basically says that U-boot couldn't find the environment configuration on the flash chip, so it loaded a default one. We can solve this in two ways: either make an environment file on our development machine, turn it into a binary and upload it to a certain offset, just like we did with the network drivers, or alternatively, we just enter save env, which will write the default environment to the correct position on the flash chip anyway, reset the board, and the warning goes away. Although our board is now booted up, it has no operating system on it yet, and apart from some very basic stuff, there's really not much else it can do. Which is why, as a sort of a teaser, I'll boot into a fit image, which was already provided by NXP. The fit image, in case you don't know, is a single file that contains pretty much everything necessary for a Linux system to boot, namely the kernel, the device tree, and finally the root file system. In fact, it can hold any number of either of these, so what we need to do is use the bootm command with the correct parameter, which is the part after the hash sign. In the next video, I'll not only show you how a fit image is constructed, but we'll also build a completely custom Linux system from scratch, so don't forget to subscribe to the channel. But for now, Tomasz from Slovenia, signing out.